keynote
Yes. Yeah.
and in full screen?
Yes. Fantastic.
All
Great.
right.
Yeah. So I'll do the introduction and then we can start. Hello everybody. Thank you for joining another Vanderbilt Machine seminar. Today we are very glad to host Jeff Clune, who is a professor of computer science at University of British Columbia, Canada CFAR AI chair at the Vector Institute, and a senior research advisor at DeepMind. Jeff focuses on deep learning and deep reinforcement learning. He has previously been a research manager at OpenAI, a senior research manager and founding member of Uber AI Labs, and the Harris Associate Professor in Computer Science at the University of Wyoming, as well as a research scientist at Cornell University. Well, Jeff has received numerous awards since 2015, including but not limited to Presidential Early Career Award, NSF Career Award, Outstanding Paper of the Decade, and a Distinguished Young Investigator Award, to name a few. He had numerous papers in top machine learning venues, NeurIP, CVPR, ICLR, and ICML, with many Best Paper Awards throughout the years. And we are very glad and honored to host Jeff today here. Jeff, with that, the stage is yours.
Thank you very much. And I want to just confirm you can hear me okay?
Yes.
Okay, great. So thank you everybody for coming, and thank you to the organizers for the invitation to talk to you a little bit about our work. What I want to do today is to go through some different types of algorithms that my colleagues and I have been working on for a while now. And we're going to start off with these, or the main topic will be these three types of algorithms here: quality diversity algorithms, open-ended algorithms, and AI generating algorithms. And I'm going to give a little bit of background on what they are and some previous work that we've done in them. And then what I really want to spend this kind of the second half of the talk, once we've set that up, is how new language models are kind of opening up lots of low-hanging fruit in these areas. It's quite exciting. So I want to start by noting that there's a paradox in life that most people don't realize, and that is that if you try too hard to solve a problem, you will fail. Paradoxically, if you ignore the objective entirely, you're much more likely to succeed. So as a metaphor for that situation, imagine you're in this maze here. Can you confirm that you can see my mouse pointer?
Yes, we can.
Good. All right. So if you start here at this circle and you only reward an agent for going closer to the goal, which is up here, that's what happens in this algorithm. You will go north and you will butt your head against the wall forever. You'll never solve the maze. In contrast, it's very trivial to solve this problem by saying, just go to interestingly new locations in this maze here, even just new locations, and eventually you will solve it. Now, you might think that that's a simple, trivial problem that doesn't show up in real life, but you would be wrong. So if you went back centuries to the time in which this was the predominant cooking technology, and you only funded researchers that would produce cooking that produced less smoke and faster cooking times, you would never invent the modern microwave, because to do that, you had to have been working on radar technology and notice that a chocolate bar melted in your pocket. Similarly, if you went to the time of the abacus and you said, I'll only fund people who give me more compute per hour or per dollar, you would never get the modern computer, because to do that, you had to have been working on vacuum tubes and electricity, which were technologies that were not invented because they help with computation. So this is all summarized in this great book by Ken Stanley and Joel Layman. And one of the ideas is that the only way to solve really, really hard problems is create the problems while you go, recognize interesting new problems, and goal switch between problems when you can. So what do we mean by goal switching? That comes from this paper we had in 2016. If you're working on one problem, like trying to get a robot to walk, and you suddenly start making progress on another problem, like crawling or standing on one leg, don't throw that progress out because it doesn't measurably improve your ability to walk on two legs. Instead, start working on those problems too, just like you might work on electricity or vacuum tubes, because they seem interesting and potentially useful, but they might be stepping stones to ultimately solve your ambitious goals. And we want our algorithms to do that, to recognize, ooh, that's an interesting new problem we could work on, and start to work on it. So that leads us to this field of quality diversity algorithms, which my friends and I have been creating for, I don't know, 15 years now, I think, maybe 10 years. And the idea of these algorithms is to, instead of produce a single high-performing solution, to instead return a set of high-performing yet diverse solutions, much like you see nature did. All of these different things in nature are extremely high quality for what they do and wildly diverse. So the poster child algorithm in quality diversity, the most common one, is this algorithm that we invented in 2015, and it's called Map Elites. And the idea here it's quite simple. So imagine we take a search space, like I'm searching for a fast robot, for example, and I will choose manually the dimensions of variation that I want to see diversity in. Later on, we figure out how to not do that manually, but for now, just imagine we pick them ahead of time, height and weight. You can discretize this space, and then you can run a very simple algorithm that basically says, hey, let's randomly initialize the algorithm by creating a random agent. This could be a parameter vector describing the robot's body and policy, evaluate it, get the traits we care about, its height and its weight, and its performance, which we're showing in color here, its reward. And then you just put that into the appropriate cell in the right height and weight. Then you run an infinite loop. You take something out of the archive. Of, this is like an archive of good ideas or stepping stones, the best stuff we found so far. Change it a little bit, reevaluate it, and then figure out where it should go in the archive. And if it's the best thing you've seen of that type in that cell, swap it in. So if it's the highest performing thing at this location, it gets swapped in. And what you do is you therefore accumulate a set of high quality, diverse solutions rather than just keeping the best thing you've ever seen. And that teaches you a lot about your search space. Like there are local optima here and here, and there's a fitness valley in the middle, etc. So we had been working before this algorithm to try to create soft robots in this simulator you see here. And we were able to produce a lot of diverse robots, but there was a trick, which is the only way we could generate diversity was to do separate runs of the algorithm. Each one produced a different type, but within the population of this algorithm, it only produced variants on one of the types that you see here. And that's not what nature does, right? You don't restart evolution over and over again to get dolphins and humans. You want one run that explodes in diversity and creates a bunch of stepping stones that can all build off of each other at the same time. And so we're hoping to push towards that with QD algorithms. So in this soft robot space, we chose these dimensions of variation. We try to optimize for speed, and you can see very low quality solutions and not a lot of exploration of the space. If you add diversity in these two dimensions, you get more performance. So diversity helps, you get some yellow, but we still don't explore the space, which is weird because we're trying to encourage diversity, but it has to trade off performance and diversity in a way that doesn't usually work very well. In contrast, with the same amount of compute, MapElites does this, which is just a total sea change in what you can see out of an algorithm and explains why QD is so exciting as a research field. So here we've learned about all sorts of local optima. We've actually discovered a better maximum because we had better exploration, etc. What's also cool is you can look into these algorithms and see the effect of goal switching. So this is an algorithm where there's actually like generations, like a parent-child relationship. And so we can take a final solution and trace back through its ancestors and say, where do they live in this two-dimensional grid of height and weight? Or in this case, it was two different traits, but it doesn't matter. The point is that to get to the best solution right here, actually right here, you had to traverse, you start here and you'd make this long circuitous route throughout the search space. And so you wouldn't have known that this is the right curriculum ahead of time, but yet this is the thing that ultimately produced the right solution, much like with vacuum tubes and electricity. So we put these ideas together in a paper in Nature in 2015. You can see the grid here. This is the actual map. And it allowed this robot to adapt to damage in about 1 to 2 minutes because ahead of time, it searched in simulation for a huge diverse set of high quality gates. And then once it became damaged, you could rapidly use a sample efficient algorithm, in this case Bayesian optimization, to search through that set of high quality diverse solutions and find a gate that still works despite the damage. We also put these ideas to use in another paper we had in Nature, this time in 2021, with these awesome authors, where we basically applied this to states within RL challenges. So at that time, almost every algorithm did horrible on hard exploration challenges. These are problems for which you have to take many, many actions before you get any reward from the system. The classic example was Montezuma's Revenge, which was an Atari game that had become kind of a grand challenge in the field of reinforcement learning because all the algorithms were so terrible on it. And if you see here, here's a bunch of previous attempts to do well in this algorithm, basically bouncing around zero. Go Explore and Contest really just blew the roof off of this problem and allowed us to score arbitrarily high scores, including beating the human world record. And the idea is that you basically want to go to as many diverse states in the game, but for each state, you want to get there in the most high quality way, the most efficient way, and also the highest scoring way. And if you just basically do that and expand out the set of places you know how to get to it in a high scoring, efficient way, eventually you find the way that solves the game. We applied it to all of the other games in the Atari benchmark, and basically solved every single game in the Atari benchmark, which was the first algorithm to do that. There's some caveats in the paper that you should check out. We also applied it to robotics. This is Go Explore in blue, putting its toys away. You only get a reward when you put your toy away, so it's very sparse. And what you can see is even intrinsically motivated PPO, which is like the state-of-the-art RL algorithm with intrinsic motivation, can't solve this problem ever, whereas Go Explore solves it every single time. So QD algorithms give you a diverse set of high-performing agents. That's quite good. They take advantage of goal switching and they're really good at exploration. So what's missing? Well, one answer is they're stuck in a single environment. They're never going to like invade new niches like animals do in Darwinian evolution. In traditional ML, we typically pick a problem like Go or Dota or StarCraft or Atari, and then we bang away on it for a while. Maybe eventually we throw a lot of compute at it and we solve that problem. But a Go playing agent is not suddenly going to go invent a new form of calculus or learn to make an omelet. And so what we want instead is a type of algorithm that my colleagues and I have been working on for about 20 years now, maybe my whole career. And the idea here is that we want open-ended algorithms. These are algorithms that literally would endlessly innovate. An example is natural evolution, which has been going for about 3.5 billion years and continues to surprise us, such as with the COVID pandemic, and human culture. So we keep going, we keep inventing new problems and solving them. Technology is not about to stop. In fact, it's actually speeding up because of goal switching, because of accumulating good ideas and stepping stones and building on that archive of past solutions. So the question is, can we make our algorithms do this? Another way to frame it, which comes from my friend Jean-Baptiste Moret, is can we create an algorithm that would be worth running for 1 billion years and it doesn't run out of steam, it doesn't plateau or converge? Because that's what Darwinian evolution and human culture, presumably, we can do. So I think one of the keys to this is that the algorithm has to generate its own challenges and solve them, and then each solution itself becomes a new opportunity, a new challenge. For example, evolution arguably came up with the challenge or the solution, or sorry, the challenge or the problem of leaves high up in a tree, and then the solution in the form of caterpillars and giraffes. And those things now become opportunities for new challenges, right? You can either eat caterpillars, you can live inside of a giraffe's tummy, you can cooperate with them, etc. So an algorithm we put out that pushes in this direction is called POET. And the idea here is to endlessly generate increasingly complex and diverse learning environments as well as their solutions. So to do this, we're now going to start doing something which was new in this paper, which is effectively to say, we're going to parameterize the environment itself, and we're going to search for environments while we're also creating agents that solve them. So to do that, we have a population of environments visualized over here, and then you periodically will take an environment out of this archive of environments, perturb it a little bit, and keep it if it's not too easy and not too hard for the current agent or set of agents, and it's interestingly different than any environment we've had before. And then we'll simultaneously be optimizing agents to solve each of these environments. In this case, we had a population of specialists specializing in each environment, but we will allow goal switching. So if you suddenly have an innovation in one environment that allows you to invade and become the best thing or the best solution to another environment, you can do that. just like a new technology in machine learning can go and invade and disrupt chemistry, for example. So every environment that you see here was automatically created by the system. And initially, the environments are quite simple. It starts out with little tiny stumps by themselves, or little tiny gaps, or a little bit of rugged terrain, and allows the agent to work on that relatively simple challenge. But as the system gets better, it eventually produces really large gaps, really tall stumps, a lot of rugged terrain, and combines those challenges together for our little robot body here. One interesting thing about this algorithm is after the algorithm itself created a bunch of environments and solved them, we went back and we said, hey, could we directly optimize an agent to solve that problem? And in every single case, the answer was no. That's ES here versus Poet. So you needed that curriculum to solve that problem. And what's even more interesting is that even if you try to hand create curricula that get from these challenges to these to high performance, it basically doesn't work. You need that kind of weird, counterintuitive, meandering path curriculum to truly solve these environments. So one of the coolest things I've seen in my career is Poet doing this. So these are all environments that were created by Poet in one run, which is pretty impressive. And here is like the tree of life, but of environments. So you can think about this as kind of the analog of like the big cats and the big dogs and the water creatures and the sand desert creatures. And so these very deep phylogenetic branches of environments that are being riffed on and created by the system. Somebody took Poet and trained on it and put it out into a real robot. They basically use Poet-generated environments for domain randomization, which allowed this robot to get out into very challenging terrain, which is very cool to see. Okay, so Poet shows us the benefits of QD again, and that we should generate challenges while we solve them. But it too, in some sense, is still stuck. Now it's creating its own environments, but it's still kind of stuck in one type of environment. So we're going to return to that a little bit later. Right now, I want to zoom way out to our most ambitious goals as a field. If you think we should make AGI, which is a subject of a whole different talk, I think you admit there's still a ways to go, although this slide is becoming dated as we make progress. But the question is, how will we get all the way there? Traditionally, we hand design all the pieces of AI and we hope to put them together. But I actually think there's a clear trend in machine learning, which is that hand design pipelines give way to learned pipelines the more compute and data you have. And we've seen that time and time again. Here are some examples. So this suggests an alternate path, and that's what I call an AI generating algorithm, where you do lots of pre-training and you ultimately search for and find and train a sample efficient agent or learning machine. And we have a proof of that happening on Earth. Okay, so Earth had a planet-sized computer 3.5 billion years, and it produced you. And you're the most intelligent thing we've ever seen in the universe. Congratulations. So we could do this with algorithms as well. And to do that, I think we have to simultaneously push on three different pillars. We have to meta learn the architectures, the learning algorithms, and generate effective learning environments all at the same time. And handcrafting the solution to each of these pillars is very slow. So why don't we just let machine learning do the heavy lifting here? So we've spent most of the talk so far going over pillar 3, automatically generating the learning environments with QD algorithms and open-ended algorithms. So now I've kind of set the stage. You understand QD algorithms, open-ended algorithms, and AI generating algorithms. And now what I want to do is talk about how frontier models, foundation models, large language models, whatever you want to call them, have totally changed the game and allow us to make exciting progress in these research areas that was not possible before. So the first paper I want to mention is called OMNI, and it was led by Jenny with these great co-authors here. And the idea here is that if we really want to produce an open-ended or AI generating algorithm, we cannot be confined to a small set of type of problems, like you see in Poet, or if you're familiar with the XLand or Ada work from DeepMind, which followed up on things like Poet. They're kind of all within one simulator, one type of task. And so what we want is to really break out and say, you don't have this predefined manually defined constrained distribution of possible environments, even within one simulator. We want you to be able to do anything. So the most or one of the most general task spaces, would be any task you could describe in natural language. And that would be really open-ended. However, then you have a needle in a haystack problem because almost everything that you generate is nonsense or too hard or impossible. And so what we need to do is figure out what are the needles in the haystack, the problems that are really interesting and worth learning on. And so we thought about this a little while, and we came to the conclusion that the task should have at least two important properties. They need to be new, and they need to be interesting. So the question is, how do we find them? Now, one thing is they need to be new, interesting, and they need to have high learning progress. Okay. We want the agent to be able to learn on them. They can't be too easy and too hard. So learning progress we've been working on for decades. We kind of know how to do that. But there's another problem, which is that you can have high learning progress, but on a problem that is not interestingly new. For example, if I gave you, the task of memorizing 10 digits of a random number, like pi, but it could be any random number, and then you did that, and then I said, okay, now memorize the next 10 digits. Well, you could do that too. And then I could say, now memorize the next 10 digits. So there could always be learning progress. There's something to learn that's not too easy and not too hard by arbitrarily tacking on digits to memorize. But that is not that is not an interestingly new problem. We don't really want an agent for 3.5 billion years to just get really good at memorizing one arbitrarily long set of numbers. So what we really need to do is figure out a way to quantifiably determine what counts as interestingly new. There's a problem though, which is that for decades, people have been trying to quantify what counts as interesting. And almost every time, not almost, every single time we have done that, we find tons of pathologies. When we try to optimize against that quantitative function, we don't get what we want, we get what we asked for. For example, if you ask a robot to find new states, well, if it discovers a TV tuned to a dead channel, it's flickering pixels, those all count as new states, but they're not interestingly new states. Similarly, you can ask a robot to produce a new trajectory of motor commands that have never been seen before, and it can just flop around twitching randomly, and it always produces new stuff. So this relates to this Goodhart's law. When a measure becomes a target, it ceases to be a good measure. So past approaches to hand coding what counts as interesting don't work. And this relates to this famous quote from Justice Stewart, which is, there are things that we cannot define, but we know them when we see them. I think interestingness is one of them. And so I think this is actually the hardest and most important problem in open-endedness is, can we quantify what counts as interesting so we can use it as rocket fuel for our algorithm? And I think for the first time in history, we have a potential answer for this, and that is we can just ask foundation models. So they already know what is interesting. They've read the entire internet, including lots of humans talking about what is interesting versus not interesting. They have common sense, and we can just ask them, is this count as an interesting new problem? And that's what we do with OMNI. So OMNI stands for open-endedness via models of human notions of interestingness. And the basic setup is we'll have a reinforcement learning agent, task conditions, so we tell it to do a certain task. And then how do we generate the tasks that it's learning on? Well, one thing is we need high learning progress. And the second question is it interesting? So for high learning progress, we use a method that came out of my team at OpenAI, which you can see in this paper. But then for interestingness, we'll just ask GPT. It's read the internet. It knows, it has common sense, and it probably knows that memorizing endless digits of pi is not interesting. So we tried it in a couple different domains. In the crafter domain, the system generates a bunch of different tasks. And what you see is if you randomly sample tasks here in red, you get no performance at all. And if you use learning progress only, that works pretty well, but it works even better to say that the task should also be interestingly different. Now here we're measuring performance after training, or actually across training, but on a hand chosen set of tasks that we ahead of time thought were interesting in this domain. And so it's basically learning a basic amount of skills that transfer over to working on a generically interesting set of tasks. Same thing for baby AI. That was in a predefined distribution of tasks, but we really wanted to go to this infinite task space where it could be any type of task describable in language. So in this simulated kitchen domain in Thor, we say, pick anything. Like the language model could say unscrew a light bulb and put it on top of the toaster, for example. The challenge is once you allow any possible task, you need what's called a universal reward, what I call a universal reward function. You need to know if any possible task was done, right? So how do you do that? Well, basically, you can just ask GPT to also provide the reward function as a little code function that will check against, in this case, the state of the algorithm and see if it was done. You could also use a video language model for that as well. So we ask it for the reward function, we ask it for the task, we train against that task, and then we repeat that process over and over again. And we're growing a library of tasks that it is good at doing. Once again, uniform selection does terribly. Here, because the task space is so large, learning progress also does terribly. And OMNI does way better because it's focusing on the needles in the haystack of interesting tasks in the space. Also, you can look across this training and see a cool curriculum. It says like first it learns how to find an apple, then learns how to find and pick up a knife, and then it learns how to slice the apple with the knife. So it's starting to put together skills, which is pretty cool. All right, so OMNI gives us an infinite task space. That's pretty good. The con is we're still just confined to whatever, one type of environment, whatever simulator we were stuck in. So what we really need, if we really want to go for the most ambitious goal here, is to run an algorithm like OMNI, but in a truly infinite task space. In fact, in my 2019 AI generating algorithms paper, I proposed that the real search space we want is what we might call Darwin complete, which means that it could express any possible environment that you could simulate in a computer would be in that search space. That is a Darwin complete search space, and that's what we want. So in a paper that is currently under review at iClear, and hopefully we'll see if it gets in, we have this algorithm called OMNI Epic, which extends OMNI, but now instead of being tasks within a simulator, it is now any task that could be programmed in code. So environments programmed in code. And here the idea is we will have OMNI literally just code up the environment. So it could say, I'm going to use the PyBullet simulator and create a world within PyBullet, or it could program its own simulator, or it could go download some other simulator that exists on the internet, or it could create math games or logic games. It could do anything it wants that you can do with code. And because many programming languages like Python, which we used, are Turing complete, now we have a Darwin complete search space because we can literally create code for any task. Now, in this particular paper, because we're a small academic lab, we're not actually letting it create arbitrary code for creating its own simulators and doing other kinds of domains. We're still going to be within PyBullet, but it's going to create the code for challenges within the PyBullet simulator. But it would be very simple to let it kind of create code for other simulators as well. But let's see what it can do. So we're going to seed it with a couple example environments. So we give it this environment here, jumping across rainbow platforms. And then now everything that you see, we seed it with that. And everything that you see here from here on out is all generated by OMNI Epic. So it first says, okay, I can move those platforms up and down. It modifies the code to do that. And then the agent learns to do that. It says I should create an environment with a ball that you kick through goalposts. I'm going to now create gaps between the platforms and have them move. Now I'm going to have you run an obstacle course, more complicated obstacle course, which you can see here. Here it touches a button to create a bridge that was invisible. Here it knocks over a stack of dominoes and has to create a chain reaction, and on and on and on. Oh, here's my favorite, a game that my kids love to play which is knock over a tower of blocks that the other kid has been making. All right. So what's really amazing about OMNI is that the longer you run it, the more diversity and more cool stuff you get. So here's a simulated run where we just assume that the robot solves each challenge so we can see what happens and like if you run it really long. And this thing is super cool. So in addition to the environments we've told you about, it creates like search through a complicated building, pass things down a conveyor belt. It creates moving goalposts. It has to have a bank shot and bounce a wall off of goalposts. It creates different kinds of dodgeball and soccer arenas. It even creates a construction site that needs to be cleaned up and then a cluttered, busy restaurant where you have to clean the dishes off of a table. And so this algorithm, for me, starts to look like an algorithm you might want to run for 1 billion years. Like, I don't actually know what would happen. Maybe it would surprise us and be able to actually go and do interesting things forever. And that's what's exciting about this research is we're starting to get algorithms that we don't know what's out there if we explore the frontier. You could, of course, have Omni also choose to work simultaneously or separately on a different robot. And so here's a bunch of really cool environments Omni Epic made for this ant robot here. And it could even customize the environments to that particular robot morphology. So to conclude the Omni chunk of the talk, I think that finally allows us to focus. I mean, Omni finally allows us to focus on interesting tasks, which had held us up for decades. And then Omni Epic allows us to generate any possible environment. And so maybe this could be something that we could run for 1 billion years and it would continue to surprise us. And if not, we would learn something about where it fails and we could focus on that. So that's a very exciting research direction for any of you that are thinking about maybe where to focus your efforts as a PhD student. Okay, I want to tell you about some other projects that I think feed into this vision. One of them is called video pre-training. This is out of my team at OpenAI. And the idea here is that open-ended learning often fails because RL exploration is just so sample efficient that it takes forever. So even if I could generate the right task and then the next task and the next task, if every single time I have to stop and learn and that takes me like 8 months of compute, then the whole process is just unbelievably slow. And so this is a giant drag on any attempt to create open-endedness. And so the question is, could we make an AI generating algorithm without a planet-sized computer? And I think the answer is yes. And I think the answer for how we could do that comes, to borrow from Newton, from the fact that AIs see further by standing on the shoulders of giant human data sets. So by pre-training on the internet, we can get sample efficiency. For example, if you wanted to have an algorithm play Minecraft, there's a ton of videos online of people playing Minecraft. The problem is that videos are unlabeled. And so you can generate like typically for text you get the next word for free then or the next musical note or the next pixel in images, and so you can do self-supervised learning. But to do that, to create behaviors in an agent, you need to know what actions people are taking at every time step. And to do that, you can actually train what we call an inverse dynamics model. All you do is you take a video from online, you give it the past and the future, and the job of the IDM model is to just predict what action must have occurred at the time step in between. So I see this and then I see this, you must have hit the jump button to cause that transition. Once that model is trained up, and to do that, you can just get some contractor data, record some people playing the game where you have the labels, and just train to go from unlabeled video to labels. Now, once you have a model that can provide those action labels, can infer them, you can go and label the entire internet. So we went and we took about 8 years worth of people playing Minecraft. We inferred the actions they must have been taken. Then we just did classic behavioral cloning at OpenAI scale on a massive transformer. And what we found is it worked really, really well. And the scaling laws all apply. So the more data on a log-log scale here, the more data you give it in pre-training, the more, like, only at very, very large scale do you start to get the ability to do things like craft stone, to find and make stone tools and make a crafting table, things that take humans about 2 minutes and 3,000 actions. And just look at these videos here. I want to particularly call your attention to the rightmost video. So this is a pre-trained agent, and it knows how to explore. So here is it exploring a village. It goes from one building, checks it out, opens it up, looks around, goes to another building. It knows how to open doors, climb stairs, open chests. So rather than mashing the keys randomly and flailing around and twitching, it's systematically performing exploration in an environment, which is how you get sample efficient learning, because now it's going to be much more easy to stumble upon rewards and figure out how to learn from that signal. So to test that hypothesis, we said we're going to fine tune on a really hard task that takes humans about 24,000 actions in over 20 minutes, a skilled human. We'll just reward everything in this trajectory here. And then what we found is that if you don't pre-train on the internet, you just try to do RL on this task, you get nowhere. That's the blue line. But with pre-training on the internet and then a reinforcement learning, you can learn each successive step in this very complicated tech tree to get all the way up to diamond tools, which at that point was a grand challenge in this area of RL that was trying to get RL to play Minecraft. It's basically human level at this task. And I don't have time to show you this whole video, but you can see this agent is quite skilled at operating in the game, including using this little user interface here, dragging and dropping icons, clicking on them. Effectively, it's a computer using agent, which was a precursor to what Anthropic rolled out a couple of months ago, which is a foundation model that can use your computer. This is the beginnings of that. Okay, I won't show you the rest of this video. It's quite impressive. So to conclude VPT, or video pre-training, it enables us to learn really hard exploration tasks efficiently, and I think it should greatly catalyze open-ended algorithms because now you can drop in a sample efficient learner as the agent, and you can imagine pairing that with OMNI Epic as the thing generating the challenges. A couple other works I want to highlight. We have Sima, which is basically doing VPT, but across many different games. So now it trains on like 13 or different really high quality 3D video games. And the most wild thing about Sima is that if you train on 12 video games and transfer to the 13th, that's this column here, you do almost as well. That's this 100% line as if you just train directly in that 13th task. So say that again, you don't even have to train in a game, and you can do about as well as if you directly had a bunch of labeled data in that domain just by transfer learning from other games. So it's learning to become a general competent agent, and imagine what that would do in an open-ended algorithm. I also want to mention this really cool project called Genie, where the idea here is that you can basically train a world model to create any interactive environment. So you give it a picture like this picture here, and then it produces like a video game that you can play and take actions in and control this agent. And here's a bunch of examples here. And if you do that, that allows you to basically play any video game that the system can imagine. That means you have an infinite amount of worlds to train in, to train your agent in, right? This is another Darwin complete search space. In fact, this is the one I put in my 2019 paper when I coined the term Darwin complete. It's just a neural net that is the entire environment. It does the transition from one state to the next based on the action that you take. And in fact, I didn't have time to do this, but we just put out Genie 2 a couple of days ago. I'm hoping this will work. Can you confirm that you can see my browser?
We cannot.
You cannot. All right. Well, I want to stop, go back to Facebook or Zoom. I'm going to do a very risky thing and share my whole screen. Hopefully that goes okay. Now, can you see my browser?
Yes.
All right. So this is Genie 2. We just rolled this out just a couple days ago. Genie 2 is the same idea, but now scaled up to arbitrarily complicated 3D games. So you can see the mouse and keyboard actions being taken by the agent or the human here. And you can ask it for any kind of world you want, like driving a sailboat on a lake and boom. And look at this photorealistic reflections off of the water. You can control the sailboat left and right. You get all these crazy games, 3D games. Let's make that bigger. And it does so many cool things. So here you can see all the like this here, this column here is if you go forward, this is if you go left, this is if you jump, and the game engine knows how to make a jump work in different environments with different robotic characters. It can generate different kinds of games like you see here. It can do like, snowy worlds and sand worlds. It knows that it should kick up dust. And I want to show you this. It can even create interactions with objects. So like shooting the barrel in the bottom here. Can you play? My internet's being a little laggy. Or exploding one of these balloons. You can walk through a door. You get to see reflections. There we go. All sorts of crazy stuff. All of this just by asking for a neural net for like a 3D shooter with explodable barrels or like a valley samurai game with balloons. And so now imagine training an open-ended algorithm. Imagine pairing this thing here with OMNI. It's pretty amazing to think about. All right, going back to the slide deck. Can you see the slide deck again?
Yes.
Good. You could do this for robotics, et cetera, et cetera. So that's pretty cool. All right, the next project I want to tell you about is called thought cloning. I don't have too many more of these, so bear with me. But I think this is an interesting innovation as well. This is learning to think while acting by imitating human thinking, which nobody's really done before. And so here the idea is that AI agents, especially our RL agents, rarely think in natural language, but thinking is what makes humans unique and allows us to generalize well and adapt well. So can we get our agents to do that too? So the idea here is we want to imitate humans thinking out loud while they act, to teach AI to think. So typically in behavioral cloning, you would just clone the actions an agent takes, like in a game like Minecraft. But with thought cloning, we want to clone the actions they take, but we also want to clone the thoughts they were having in their head while they were taking those actions. They're planning and they're reasoning and they're replanning if something doesn't go according to plan. And I don't have time to go into the details, but in little toy domains with simulated thought data, what we show is that if you clone actions alone, that's orange, you eventually can do quite well. But if you clone the thinking behind the actions, the reasoning, then you can learn way faster and ultimately also converge to a higher performance. That's blue. What's also cool is that as you change how far out of distribution you are, that's on this axis here, then behavioral cloning starts to fall off a cliff as it gets out of distribution. This is zero shot, whereas thought cloning does a much better job of handling new environments and gracefully degrades performance better. And in few shot cases, if you fine tune in the new environment, behavioral cloning jumps up a bit, orange to orange, but thought cloning jumps up a lot more. So the size of the jump when you're way out of distribution is bigger with thought cloning. So it's a better at out of distribution generalization and at learning out of distribution because it is basically thinking in words and can replan just like you think and replan when you're in a new situation. Another benefit to thought cloning is that the agents are quite interpretable. So, it'll tell you what it's about to do and why. And so, for example, if it's stuck at this door and not moving, traditionally with a black box neural net, you would have no idea how to debug it. You don't know what's wrong. You don't know what it's thinking. Whereas with a thought cloning agent, it says something like, oh, I can't open the door because I'm going to wait for the person to move out of the way. And you say, oh, it doesn't know that movie posters have pictures on them. I'll add more training data on movie posters so that it doesn't get distracted by them. Similarly, this is really important for AI safety, which I take very seriously, because you can watch the agent think and get a sense of how safe it is or stop it if it's about to do something unsafe. So if it says like, I'm going to open this door even if a child is in the way, then you could stop it before it does that. So that led to this idea of something called pre-crime intervention, which is a nod to Minority Report, which is basically if the agent says it's going to do something that we don't like, we can just stop it. And as a little test of that, after training, we decided that, hey, touching red items, for example, is an unsafe behavior. If you say you're about to touch a red items, we halt the program, and you can see this dramatic reduction in the amount of times that it touches red things. So it's quite good for AI safety. This is a bug that should say the AI scientist at the top of this slide. This is a project we just put out a couple of weeks ago where we're trying to completely automate science because science itself is the ultimate open-ended domain. And can you have an AI agent that's basically using all of science as its world, as its problem space to innovate forever in, much as real scientists, humans try to innovate forever. And we think the answer to this question is yes. So we created this AI scientist and it can generate its own ideas, design and run its own experiments, analyze and visualize the results, which you can see here, write an entire manuscript, which you can also see here, the visualizations and the full LaTeX. It can peer review its own manuscripts to see what's good and bad, and anything that it thinks is good enough, it can kind of publish to its own internal archive, and that then serves as a bunch of stepping stones, discoveries it's made. It can then read its own papers, its own discoveries, build on them, and conduct new research, just like a scientific community. So in that project, we did it with machine learning itself. So it's conducting actual machine learning experiments, coming up with new algorithms, new architectures, etc., picking its domain, doing the science, writing it up, and then building on those discoveries. So we're terrifically excited about that. I believe this is the final thing I'm going to tell you about. It's called the Automated Design of Agentic Systems, done by these wonderful colleagues. And here the idea is that we can have AI generate its own agentic systems. So nowadays, people are basically creating what we call agentic systems. They're like workflows with lots of calls to language models and other tools. So like GPT-4 using chain of thought reasoning or reflection and maybe doing a web query or maybe going out to Google Scholar and then analyzing its results, maybe writing some code, generating a plot, looking at the plot. And you have this complicated workflow that tells it like what to do and how often to check its own reasoning and to peer review itself, whatever. And so you can either hand design those workflows, which has been working quite well. Almost every agent you've seen is one of those hand designed workflows. But of course, the lesson of AI generating algorithms is that hand designed pipelines give way to learned pipelines as you have more compute and data. So you can just search for these workflows as well. And so we just have a library of agentic systems we've already discovered, and we take one off, we change it a little bit, and then we try it out. And if it's better, then it gets added to the archive, or if it's interestingly new, and we grow up the set of agentic systems. And eventually what we show in this plot here is that the blue line here, which is ADAS, the automatic design of agentic systems, comes to learn things that are way better than all of the hand-designed agentic systems like chain of thought and reflection and all the stuff that people have been building by hand. And it starts to kind of come up with interesting ideas and building blocks and build on them over time. The font's a little small here for you to see, but you can check the paper. And here's one example agentic system we designed that performed really well. Okay, I want to quickly mention AI safety. I think this is an unbelievably important topic. I take it very seriously. I've written on it with Bengio and Hinton and Daniel Kahneman and others saying that AI is very dangerous. It has a lot of upside, but also a lot of potential downsides. So we want to make sure we develop it as safely as possible. There's also unique safety issues when you're doing self-improving AI generating algorithms, open-ended algorithms, etc. And I have written about those topics in these two papers, which I encourage you to see. So overall, I think it's inevitable, in my opinion, that we're going to develop AI, and we just want to make sure we do it safely so we get to maximize the chance of upside and minimize the chance of downside. Okay, 3 conclusion slides of the talk overall. I've introduced quality diversity algorithms, which explore well, create and collect stepping stones. They can harness goal switching, and they invent their own curricula, which is often counterintuitive. I've also introduced open-ended algorithms, where the goal is to create an algorithm that literally could innovate forever for billions of years, like natural evolution and human culture. And a specific example of that, when it's applied to trying to bootstrap up intelligence in AI, is an AI generating algorithm. I actually think that's the fastest path to AI. And so it's exciting to work on. It's also an amazing time right now to be an AI generating algorithms or open-endedness researcher because foundation models get to stand on the shoulders of giant human data sets. They know a lot of common sense and intelligence from humans, including a sense of what's interesting, and we can use that to catalyze these open-ended algorithms that we're creating. And you saw examples of that in OMNI Epic, which can finally pursue what is interesting and do it in a Darwin complete search space. We saw it with VPT, where we can basically take all of human data, inject it into an agent, and they now have a seed agent that is a sample efficient learner to kick off the process. It's kind of like skipping all of evolution up until the point where you have the human brain. We saw thought cloning, where we can literally train an agent to think, which is pretty cool. And now we're seeing just like a proliferation out of my lab and other labs of people putting these ideas together in wild and crazy new ways, such as with the AI scientist, the automatic design of agentic systems, Genie 2, etc. So there's just so much we can do now. I feel like frontier models have kind of opened up an orchard of low-hanging fruit, and we're all just rushing in and picking all this wonderful fruit. And there's so much more to be picked for a long time. So come join us in the orchard if you are interested in working in these ideas. With that, I want to thank the organizers for the invitation, all of you for listening, and my wonderful collaborators who've done all the hard work here, as well as the funding sources. Thank you very much.
Fantastic. Thank you so much, Jeff. We have some time for questions. There are a few questions in the Q&A. Maybe we can start there.
Sure.
Yeah. So there.
If you don't mind, I'll let you read the questions and I'll just answer them. Or people can, if they're here, they can ask the questions orally as they like.
Sounds good. Himanshu asked about training an agent for cybersecurity. Imagine you're training an agent for cybersecurity, which could be utterly complex due to existing diversity and complexity of computer networks. Could goal switching algorithms be useful here in the cybersecurity domain? And what could be some examples of those algorithms?
Yeah, it's a great question. I think the answer is unambiguously yes. I first just want to say that's very dangerous stuff to be working on. So if you're working on that, make sure that you're doing it for the right reasons because you're trying to defend against it as opposed to release new malware. And you're make sure you're sandboxed and you're very, very careful not to release something into the wild. But yes, if I was working on computer security, I would absolutely be using these kind of algorithms. And one way to think about it is put every single computer system and every piece of software you can imagine inside of a giant archive of challenges. Yeah. And then the system itself, it could solve this challenge and then this challenge and this challenge. And as it gets better at solving this challenge, that might allow it to suddenly start hacking this piece of software or exploit this um, version of this browser, etc. And you basically, the more stepping stone tasks you have, the more you can kind of jump around and learn skills that solve this and then this and that, and that unlocks something that can solve this thing over here. You could also pair it together with something like OMNI Epic, where it's generating the challenges as you go. So maybe it's creating new code that has new vulnerabilities. At the beginning, the vulnerabilities are really simple, and then it starts to harden them over time. And eventually, you're playing a cat and mouse game of Defender inventing new and like patching stuff and inventing more reliable code, and then you're the hackers trying to hack into the code. And like all of these dynamics that we've talked about would exist in this sort of a system. And it'll work better if you're doing it in uh, an open-ended way with an archive of attackers and defenders, rather than just having a normal self-play system that has kind of the best current attacker and the best current defender, because those things can basically run into lots of problems. They don't get goal switching. So I think that was there a second part to the question I didn't get to?
I think that's pretty much it. The goal switching that you kind of mentioned that, so I think that's pretty much it.
Okay.
There are multiple questions, so I move fast. Himanshu has another question about the novelty of tasks in foundation models. So how do we know whether the interesting task generated by the foundation model is actually a new task? And that is across multiple agents, across switch goals. This is something interesting.
Yeah. So basically, you just ask the foundation model. So putting aside context length difference issues, you just give the entire archive, every single task that has been proposed and solved so far. You just give it to GPT-4 and you're like, all right, now we have a new proposal. Is this thing interestingly new versus those? And it gets to judge. And it says, okay, you've done all these things. You're proposing this. No, this is actually very similar to these two things you did. Or it's like, yeah, that's completely new. Now, if you don't have infinite context length, you can do something pretty cool, which we do in our paper, which is you say, okay, I have proposed a new task. Yeah. And so now what I will do is, well, sorry, take a step back. First, I want to propose a new task. So how do I do that? I'll pull a task out of the archive. And this will be kind of our, like almost like the parent in an evolutionary algorithm. And the goal is to like change this a little bit. But I don't want to change it and reproduce something I've already produced. So let's go into the archive and get like the k nearest neighbors from the archive using embedding search or something. So now I have like the 5 things in this space. And you give that to the algorithm. Like here's like a little tiny niche of problems we've been working on. What is an interestingly new version of this? And it'll generate the next new thing. But then you want to make sure that that new thing is not something you already had. So once you have the new thing, you then go back to the archive and you find the k nearest neighbors of the new proposal. And then now you have a set of things. You're like, hey, we proposed this task. Here's the closest stuff to it. hey, language model, does this new thing actually count as interesting? And then the language model can decide yes or no. And if you think about it, this is very much what happens in like in science with like grad students, right? You read some papers, you propose a new idea. Then if you are smart, before you go and spend a year on that idea, you quickly do a literature search to see if the new idea you have come up with has already been done. And if it's interestingly new, then you go work on it.
Right. Yeah, thank you. That's awesome. I'm going to inject my question as a piggyback on that, right? So since we both actually worked on L2M, DARPA L2M lifelong learning machines, so I was quite interested to know what about the positive transfer and negative transfer? That's something that's missing from the picture right now. So we can generate interesting tasks, but how do we know that these tasks are going to actually positively transfer knowledge to the agent? So the agent is going to actually improve by learning these new interesting tasks. So can there be an interesting task that actually induces catastrophic forgetting of the on the agent?
Yeah, great question. So right now we're just kind of leaning on the language model itself to basically make a guess. Like if I baked into the request for a new task is we want you to make a task that is interestingly new and will have high learning progress. So it's just guessing that you will be able to learn it. And the fact that it's interesting means that the task that you learn should probably help out with other tasks that we consider useful. It's not going to have you memorize arbitrary digits of pi. Now, once you go learn that task, there's two issues. One, did you actually use a skill that ends up being relevant to other skills? That's a little bit down to whether or not the language model was good or not at its prediction. And you could fine tune it to get better at that over time. The second challenge is, as I was learning that new task, did I catastrophically forget other tasks? That brings in the whole DARPA project that we worked on together on continual learning. And in this project, we're not directly addressing that. We're assuming you kind of figured that out. The simplest thing to do is just to simultaneously train on all the tasks that have ever been generated, but that's very compute expensive. In the limit, if we could never solve catastrophic or continual learning, then we wouldn't have to do that, and we could have a sample efficient way to learn the new tasks without forgetting the old tasks. But that's a different talk.
Great. So there are a few more questions in the Q&A, but I know that we're at the
I'm happy to take them. I'm happy to
okay,
take them.
fantastic. So there's a question about some anonymous attendee is asking your idea about the next generation of foundation models or agents that may have different components, modules like, for example, a cognitive core for thinking and reasoning skills like human brain. Um, I'm not sure if I understand the question. um, and then there's a second part. I
I
mean,
guess
if
with this, suffice it to say on that real quick, so far every agent we've been training has been from scratch, like a neural net trained from scratch in the old school RL way. You could also use a foundation model itself as the seed agent to start solving these problems. And it could therefore also start and be intelligent in that way. And it would have to the extent that GPT-4 has a cognitive reasoning capability, then your agent has that as well. So putting all these pieces together, this is why many people, myself included, think AGI is around the corner, because you can start to put all these pieces together and really powerful things are going to happen.
right. And there is a second part, which I think would be interesting to a lot of attendees here. So they're asking for advice for junior reinforcement learning researchers about research directions that you think are appropriate to work on, especially those who don't have substantial computational facilities these days.
Yeah, that's a good question. So, I mean, continual learning is one. I think that's something that not enough people are working on, and you could do that and test that in small settings. Um, and I think, I mean, you could basically look at my career, putting aside the work that I've done with OpenAI and DeepMind, almost everything we do, we're doing on pretty lightweight compute budgets. So, if you go look at OMNI, for example, even thought cloning, these things are done on academic budgets. And so I think the idea is you should have a big, exciting idea that is what I call true path. It might really go the distance and be the right idea that could be the foundation for future generations of research. But once you have that idea, you might know that it's not going to really shine and sing until you train it at scale. But can you think of a simple way on a simple domain to show the idea and that it has value? So for example, both Omni, we didn't end up being able to train it with OpenAI compute to and like Omni Epic to go do what I really wanted to do, but we could show it on a small little domain and little tiny simulator. Similarly with thought cloning, I'd love to train it on all of the captions for every YouTube video, like what people are actually saying while playing video games. But we don't have the compute for that. So we created a synthetic domain and we created a way to get synthetic thought data. And we kind of showed the benefits of the idea at small scale. And then the hope is that bigger labs will take that up and run with it. And I've seen that happen. I've seen like the industrial labs take up ideas like this and then scale the heck out of them.
Um, Maybe two more questions. So when talking about poets, you mentioned that hand optimization failed. Do you have any ideas as to why that fails? And can we learn from the automated optimization to be better as human problem solvers?
No, we can't learn that.
Right.
So I highly encourage you to read Ken Stanley's book and Joel Lehman's Why Greatness Cannot Be Planned. The whole, like you can hear it in the title. You can't plan for greatness because you don't know ahead of time that to make a computer, you need vacuum tubes and electricity. And you don't know ahead of time that to make a microwave, to make faster cooking technology, you need radar. You need research into radar, like which was being built for like military detecting ships and stuff. The whole point of serendipity and scientific discovery is that we don't know the path to breakthroughs. And we do basic research, we discover stuff, and ultimately you find cool ideas, and eventually they unlock your biggest ambitions. And that's exactly why direct optimization didn't work. Because right now, if I gave you the goal of making a time machine, you would have no idea how to start. And what am I going to do? Fund you every quarter? Like you're going to set OKRs every quarter for like progress towards your time machine? It's a silly exercise because you don't even know what direction to head in. Like if we ever build a time machine, it won't be because we saw the path and just went after it, at least from where we are now. We're just going to do a bunch of basic science and eventually we'll discover some cool new physics that will allow us to do that.
Yeah, that's a beautiful perspective, and that's the beautiful nature of science, right? Like you don't know what to expect, and like it's incremental, but then like as a whole, it's moving forward in unpredictable directions. Yeah, very
That's
well.
right.
Yeah.
Now, what's so cool is that you can take that amazing story and put it inside of a computer algorithm to harness that power and do basic science in an arbitrary domain. That's like the beauty of AI generating algorithms and open-ended algorithms. And what I just want to say is like there's been about 5 years really that we've really been like developing this toolkit. And we every time we go and apply it to something like that robot or Montezuma's Revenge or Omni Epic or ADOS or the AI scientist, like this recipe, it works. And so it's very powerful. And I would encourage you to just try it in your domain. Like the cybersecurity one, if you do the safety thing right, and you're doing it for the right reasons, it will be very powerful there.
Absolutely. Uh, and maybe one last one for your video game-based demos. Is the AI also learning the animation and kinematics, or were those just added in?
For Genie 2,
Yeah, I believe so, right?
yeah, I'll just say, so for Omni Epic, it was generating code that describes a little simulated world with objects, colors, a reward function, and then the agent plays it. So it's like using like a physics simulator, but the specific setup has been coded by Omni Epic. In Genie, it is literally a neural net. You give it a frame, like a picture of a world and an action, and if it will just step and create the next frame of the world, and then you take an action and it generates the next frame and the next frame. So the entire world, all of it is invented in the weights and the activations of a neural net. It is just like a video game generative model. That's Genie 2 and Genie.
Fantastic. Well, in the interest of time, I encourage all our attendees who still have questions to reach out to you, Jeff, if that's okay. And then, yeah, let's once again thank Jeff for this fantastic, thought-provoking talk. And we really appreciate your time. Thank you so
Thank you
much.
very much. And also, if people are going to be at NeurIPS, I will be. It's here in Vancouver. So if you see me at the conference, feel free to come up and say hi.
Fantastic. Thank you.
All right. Thank you, everyone. Bye bye.